Okay, let's get started. So I have your midterm threes up here. In general, I wasn't that happy about the test. So the average was considerably lower than I thought it would be. A lot of you are missing the fundamentals of things we've already covered and already tested on. So if like some of you, when I say declare this function that does this, some of you didn't declare a function, just wrote a main and then cin some things. Not what I intended. So look at the solutions, look at the past midterm solutions, and see where you're missing points. But I thought, well, this is not really representative. So what I did is I essentially just moved grades up. So if you look at the main web page, it has the original grade distribution, and then I did some altering to the numbers, and then I put a new grade distribution. And then, so we're sticking with that one instead of the old one. So the grade on your test is not your actual grade, it's the one that's recorded on Blackboard. Okay? So, but are there any questions about the test itself? Or anything related to it? Any other, yeah. I can't hear you. So the calculation I did was essentially, I can't say exactly what I did, but what I did is I wanted the people at the top to not have to get too many points because they already got a lot of points, but I wanted the people in the middle to get more points. So that's what I intended to happen. But so some people's grades went up by like 5 points, some went up by like 20. So it depends on the score that you got. But it was the same thing for everyone. Other questions? Any questions about anything else? So I put up a tentative number to letter grade on the announcements page so that you can check and see where you actually are. Any questions though? Okay, so last time we started talking about these pointer things, and I said that I don't use any pointers in my code. And so you may be wondering, okay, why the heck is he even teaching us pointers in the first place then? If he doesn't even use them, why should I even use them? So what I wanted to do is deviate from the slides themselves and talk about something more interesting, that I think at least, that justifies why I don't use pointers and then why you should care about pointers. So what is a pointer? Yeah. Right, it points to memory address, so the thing itself, the pointer itself, is an address. It doesn't contain any data other than the actual address itself of what it's pointing to. Okay, so something completely different, it'll seem different, but it is actually very related. So when I click run on C-line or whatever I'm using to run my programs, what actually happens? So where is the program stored before I even run it? Before I even do anything, where's my program stored? Not in your brain, but on the computer, where? What's that? Yeah, in long-term storage, in other words, hard drive, solid-state drive, whatever. It's in secondary storage. When I click run, what happens? Right, it goes to main memory, and then our mental model, as we have understood it so far, is the CPU says, okay, fetch me the next instruction or data or whatever from main memory, and then it's going to go to main memory, fetch the data, and then feed it into the CPU where it does the decode and then figures out what the next instruction is. Great. If that's what actually happens, none of us would use computers. Anyone know why? if that's exactly what happens, you go all the way to main memory and then you fetch a piece of data from main memory, we wouldn't use computers if that was the world we lived in. Anyone know why? Yeah. It's super slow. So we think, well, RAM is incredibly fast, but in fact, it's incredibly slow. So what people realized is, okay, we can have this a giant amount of memory, which is relatively slow compared to anything else we could do, compared to the CPU, but it's faster than the hard drive solution. But if we shrink the amount of memory we use, there are advantages that we could use to access a smaller amount of memory faster. So what inevitably happened was that there's this level of what are called caches. So C-A-C-H-E, not C-A-S-H. So a cache here is the same idea as main memory, but it's much smaller, okay? And faster. So there typically in most modern computers are 3 levels of caches. So level 1 cache is right here. So you can see there are 2 of them. One of them corresponds to data, and one of them corresponds to instructions. Level 2 is a bigger amount of memory than level 1, so it's a little bit slower than level 1. And then level 3, if you have multiple processors in your system, is typically shared among all your processors and is even bigger, but also slower. And then way out here in the wide, wonderful world out here is main memory somewhere. So what happens here is, okay, I want to fetch something from main memory. It's not in any of the caches. So what it tries to do is it looks in the caches first and sees, is it already in the cache? If not, then I have to go to main memory. So let's just say it has to go to main memory and it fetches some data over to the CPU. Does anyone know what else happens when it fetches data from the CPU, from the main memory? Typically what happens is that same piece of data is copied into the caches. Because what happens is, if you're accessing that memory element somewhere in main memory, very likely you're going to access this next element or the one right before it, or data right around that element. And then what the processor is going to do is try to predict your pattern of access of memory. And so what it's going to do is it's going to prefetch some memory and then feed it right into the caches. So maybe I have to fetch memory once from main memory, but then the next thing I want to access is right in the caches, so it's much faster. So, yeah, I'll get to that in a second. So why do I not like pointers? So remember, a pointer is an address itself. So is the address of some pointer necessarily right next to that where the pointer is? So like if I have a pointer which points to address 8000, is the pointer storage, where the pointer is stored in main memory, around 8000 address? Or could it be anywhere else? It could be anywhere else. So a downside of pointers is that if you're trying to look at some pointer and then go to the memory location of where it is, it's not right around where you just access the pointer itself. And so therefore, pointers can actually slow down your code. So that's one of the reasons why I don't like pointers. But I want to, and actually we can see how big our level caches are. So I actually ran a command here on Unix systems called, I guess, syscontrol. And so it gives you pretty much any statistic about your system that you care about. So if I search L1 here, then if we zoom into, or try to zoom in here. So it says the hardware's level 1, so the I here stands for instruction, and then the D right here is for data. Cache size is 32,000 whatever. Anyone know how big that is? 32,000 what? is actually 32,000 bytes. So it's 32 kilobytes in size. Anyone remember kilobytes? Way back when? So this is not a lot of data to work with. And so level 2 is a slightly bigger. Level 3 is even bigger, but it's still tiny in size. So being able to maximize the cache usage will speed up your program quite a bit. And pointers are not a way of doing that. So then why does anyone even use pointers if it just sucks so much? So I thought, well, how does a program's allocation in memory actually work? And so this is a simplified version of how your program actually works. So I'm not going to go into all the details, but what happens is, let's just say you're going through the main function, and then you're going to call another function, and then at some point return back to main, maybe call another function, and then come back. So this stack up here actually keeps track of where you are in the memory, and then any arguments to the function that you need. So maybe let's just say we have a function called f, and then we pass in an int and a string and a double or whatever. So what happens is, when I'm going to go call that function, I'm going to put into this stack as it's growing down right here, I'm going to put there the 3 arguments that I need, the integer, the string, and the double right there in the stack. And then when I call the function, it's going to do some stuff with the stack, maybe allocate a little bit more. And then when it returns, it's going to remove those things from the stack. Great. So all of the structures, pretty much, that we have been dealing with are stack allocated. Okay? So if I declare an array of size 1,000, for example, that is allocated on the stack. So how does a stack actually work? So if I'm putting things on the stack, it's going to keep going down like this. And then if I need to access something else, I'm going to need to put all of those things off of the stack again. So I put the 1,000 argument element on the stack, the array, and then if I need something back up top, I need to put everything else away on the stack. So how is a pointer variable initialized? So in general, we're going to see a technique where we're allocating things with pointers on what is called the heap. So they're not stack allocated anymore. So a pointer variable, the pointer itself is in the stack, but the data corresponding to the pointer of the thing that's being pointed to, that's in the heap. So if I allocate like a 10,000 array size array and then put it into the heap instead, then I avoid this issue of having to take things off of the stack repeatedly to access other things. So that's actually one of the nice things about pointers, is that, well, you avoid this stack problem and it increases performance in some ways. But why would allocating something in the heap down here decrease performance based off what we talked about before? So if I load some data and put it into the stack right here, so the system, remember, is going to take adjacent elements and then put them into the caches for me. So putting something into the stack here is actually quite easy. But if I have something from the heap, that could be at an arbitrary address. And so therefore, I will suffer from some performance problems. So the key from all this is that there are some advantages to pointers and some disadvantages to pointers. Yeah?
So whenever you are accessing something at the bottom of the stack and your computer needs to remove data from the stack, where does it put that?
So we're not actually concerned about that, but typically what happens is that it's taken back out to main memory, and then, or the caches if it fits, but it tries to put it into some storage where I can access it at some later point. Because here, it can't allocate it on the heap, because if you're stack allocating something, it has to be on the stack. It can't be on the heap. And so therefore it has to put it somewhere, and memory is a good place to do it. Other questions? Okay, so let's actually talk about pointers. Yeah, so pointers, remember, the pointer itself is just an address, nothing else. It's just an address that can point to any piece of data. So if we look at this right here, this definition, the int out here actually almost means nothing to the pointer. So remember, the pointer itself is an integer, nothing else. Well, the pointer itself is an address, but an address is an integer. The int here means, what am I pointing to? Not the pointer itself. What am I pointing to? So this says I'm a pointer, which is an int, which is pointing to an int somewhere else in memory. Okay? And then if we do this, then remember, let's just say that we have an integer called num. And then if we take the address of num, that's the address of num, and so therefore I can assign it to the pointer because the pointer itself is an address. Oops. And so therefore, if I declare a pointer here and I say the pointer itself is equal to the address, now intputter is pointing to where num is. Intputter itself is the address of num. Okay, all it is an indirection. Okay, but if I call star on the pointer itself, just the pointer, then what that happens is it goes to that pointer and the star dereferences that memory location, meaning I get the value at that memory location. So inputter is at some memory location for A00, and then the star, if we put star on it, that actually looks up the value in that memory location. Okay? And we can assign some value if we put the star here, because this is just a reference to the value here. So this is just the value at that memory location, and then we're assigning 20 to it, so this will change from 25 to 20. Any questions on how the basic idea of how pointers work? Remember, pointers are just addresses, nothing else. And then the star on a pointer will dereference that pointer, meaning that I get the value at that memory location. So all it is an indirection to access some other data. So, well, why would we even care about pointers? Well, other than the reasons I've already talked about. So if we have an array right here, just a normal array, you can use a vector if you wanted to. And then if we print vals, remember we can't just print an array like this, because, and we saw what happened was we printed the memory location of where the start of the array is. So if vals is at some address, say the same one, then if we print vals, that's just the pointer. So vals itself is a pointer. Okay? And so right here, then we'll just print the memory address. But if we call vals of 0, as we have seen already, we print the value at this memory location, which is the first index into the array. So index 0 in the array. But if we try this with star, so vals itself is a pointer, then couldn't we just use the star on the pointer itself, just like we did before? In fact, we can. So if we do star on vals, this will dereference the pointer vals, and then it'll print the value at that memory location. Well, remember, the array name itself is a pointer to the start of the array. So the start of the array is right here at this address, but right here. And so what'll happen is when I call star on this thing, it'll dereference that memory location, that single memory location, which is 4 in this case. But I can assign one pointer to another. So vals is a pointer. I can assign to a different pointer if I wanted to. So what ends up happening, let's just think about what really happens here. Let's make a new document. So let's see. So the vals here is at memory location 4A00. And then we're calling val putter right here to be equal to, so that's assigned to the pointer vals. So what is val putter pointing to then? Because val putter is a pointer. What is it pointing to? What memory location? The start of the array, which is, in this case, 4A00, yeah. So val putter, because I'm assigning so it's assigning the address to a pointer. So the address, which is 4A00, is assigned to this pointer variable. So now the pointer variable has that same address because I assigned it in the previous statement here. And then because of that, val putter and vals are really the same thing because they're pointing to the same place. But question for you, are vals and val putter themselves in the same memory location? Not what they're pointing to, but are they in the same location? No, because I'm making a new pointer right here. So what ends up happening is I have vals over here and val putter right over here, and they're pointing to the same place, okay? And so that creates interesting issues that we'll see later on. Like we have multiple things pointing to the same place. And so that may cause some issues down the line. But the key here is that if I use the square brackets on the pointer itself, that works exactly the same as we have done it so far. What if instead I did, instead of this, I did vals of 1 and I did the reference right here. So what is going on? I'm looking up vals 1 and I'm looking at the address of where the vals 1 is, which is the 7 right here. So what is val putter pointing to in this array? What value in this array is val putter pointing to? Not the address, the location. It's pointing to 7. Right. So I'm assigning the address of some memory location, which is the 7 here, or the address of the 7. And then val putter, of course, is now being pointing to that location. Okay. So if we look at this, so this will answer one of the questions we had a few weeks ago. So do the same thing as before. What if we did, so val putter right here is pointing to the start of the array as before. But what if we did val putter plus 1? Oops. Val putter plus 1. Well, what actually happens here is the compiler says, okay, plus 1 means we're going ahead one whole memory location. Well, what does one whole memory location mean here? Remember, val putter is pointing to an int. Okay? How big is an int normally? 32 bits or 4 bytes. Right. So val putter plus 1, the plus 1 is calculated to be 4 bytes ahead of where val putter is. So if I look at, let's go back here. So let's just say we're assigning 4A00 like before, and then we look at cout, how about let's just cout the putter plus 1 and not dereference it, just the actual address. What's going to be printed here? So remember, we're going ahead 4 bytes, not 1 byte, 4 bytes here. So what will be printed here? So what is 4A00 plus 4? Can anyone do hexadecimal arithmetic in their head? It's actually 4A04. So let's actually test this. And I just did that out of my head. I'm not actually sure it'll work. I hope it works. But let's just see. So let's just fix all this. Get down to here. So let's make an int putter is equal to 0x4a00. And then maybe there's an error here. Okay, I see what's happening here. So let's actually make the vals is equal to the array that we talked about before. And then we'll point it to the beginning of vals. And then we're going to see out, let's see. So it'll be putter plus 1. And then a new line for our convenience. So let's see what actually happens. Actually, I should see out the actual original pointer first. Oh, come on. Sea Lion, why you do this? So let's actually see what happens. Okay, yeah. So so this is the address of vals, whatever it is. And then let's see. What does C in hexadecimal correspond to? So 0 through 9 are the same. A is 10, B is 11, C is 12. So what is 12 plus 4? 16. And so it's base 16, so what actually happens? It modulo 16. So there's no remainder when you divide by 16, which is why we have the 0, 0 at the end. Because the F here corresponds to value 15. So when I add over here, 12 plus 4, I'll get 0. Carry of 1, 15 plus 1 is 16, and so that becomes a 0, which is why we have another carry. A plus 1 is B. So 10 plus 1 is 11, and B is 11 in hexadecimal. So we really do get plus 4 in the memory location here. What if we did long instead? I'm actually curious as to what happens. So let's actually see what happens. Oh, so we actually get 8 bytes there. So from this, we can conclude that the size of a long is 8. So they're actually very smart here. This plus 1 can mean a completely different thing, depending on the type that you use. But it'll calculate it correctly based off of the size of each of the elements. So long here is 8 bytes. So it's looking up 4 here the first time. And then 7 is 8 bytes later. So that's why it does a plus 8 right here. Okay, and then if we did a plus 2, that just does the same thing again. Yeah?
Are you allowed to set the pointer equal to an actual address like you tried to do the first time?
I think you can. Let's see. So I think you can. Maybe I can do this, or not. There is a way, but I'm not sure how to do it. Yeah, you can. So you can set a pointer to realistically point to any memory location. I just don't remember how to do it explicitly. But you can set it to any variable that you want, and you can offset it any amount you want, pretty much. So that's pretty cool. So we can actually, what if we wanted to do plus 3, which is, well, 11 is the plus 2 place. Maybe let's dereference that place and then see what was there. So it got 4 correct. So it's looking up in the memory location past 11, past the end of the array, and there's no bounds checking. So we can actually be malicious here if we're writing a program to try to thwart some system. We could try to just keep adding to this pointer and then just keep printing the contents of the memory along the way, past the allowed place in the memory, which is pretty cool. Pretty scary too. But any questions about how this works? Yeah. Yeah, so I can loop through the array in this exact same way. So if you actually look at some of the algorithms that we've seen, so like there's a function in the standard library called linear search. And so what happens there is it actually uses dereferencing pointers along the way. So it takes 2 pointers, and then it dereferences the value as we're going along in the array. So you can definitely use the pointers and dereferencing along the way if you want to loop through it. But of course, as we can see here, you need to put a bound on how far you can actually go before you get into this mess. Any other questions? Okay, so let's continue. Here you must use why must you use parentheses in these 2 expressions right here? What if I just remove the 2 parentheses? What actually happens? So to make it clearer to see, yeah. So what happens is it'll dereference first, then add 1 to the value. Remember, dereferencing gives you the value at that memory location. So if I did this, oops, let's go back to the +1 version and then remove all the parentheses and just see what happens. So it actually prints the value at that memory location, then does the addition. So putting parentheses on here will more effectively communicate what you actually want it to do. Maybe you want to do this, but more likely you wanted to put the parentheses in. Okay, so we can access and set elements in an array in a very analogous way. So we can do the one we've always been doing so far, but we can have a pointer, a normal pointer as usual. What is interesting here is the way that these are done, these first 2, is exactly what the last 2 do. So when you do the square bracket 2 here, what it ends up being compiled is a pointer dereference and the plus some number offset. And that's what actually happens. So here what we can do is at index 2, we can dereference that place, wherever it is, and then set 17 into that memory location. And then we can do the exact same thing with the pointer because vals itself is a pointer. So so this one is much better to read, but what actually ends up happening is the last 2. Yeah, this is exactly what I just said. Okay, so pointer arithmetic is basically what we just saw. So we can do a +1 or -1, which just shifts the pointer to some location based off of the size of each element. So if it was int here, which is 4 bytes, ++ means move it forward 4 bytes, -— means move it back 4 bytes from wherever it was. So nothing surprising there. And then we can do += -= exactly the same way as we've been using them. Yeah, so this is something we've already done. This is effectively doing the same thing. Yeah, so it moves valputter up 2 places in the array in this case. And then we can subtract pointer locations because remember, a pointer, remember, is just an address, and an address is just an integer. So we can subtract integers, multiply integers, we can multiply memory locations, pointers, whatever you like. They're just integers. There's nothing special happening here. Okay. So how do you even make a pointer in the first place? So the way that we saw doing this was I make a star right here with the name of the pointer is equal to the address of some variable. That's the way that we've been doing it already. But there's a really, really, really wrong way to do it. But you will encounter this if you use C++ enough, so you might as well know about it. Int star putter, if you can't initialize it right now, you have to set it to something. So the typical way of doing it is using this null in all caps. So if we actually try to do this, it will work, but it's not something that you should do. And I'll explain that in a bit. So you can actually see it's in dark green here. Anyone know why? So if we actually control click and then go into the standard library, I actually haven't done this, so I don't know how far down the rabbit hole I'll go. Okay. Let's see. Okay, so if you actually look up what capital N, capital U, capital L is default initialized to, it's actually something called a macro, but it's essentially equivalent to 0, okay? So a pointer that's set to 0, if you try to dereference it, will crash the system, okay? So if you try to, not the system, but will crash the program. So if we try to see out putter right here, maybe this will work. I'm not sure. Oh, yeah. It actually did crash, but can you tell why or how it crashed? Yeah. What is this exit code? Anyone seen it already? Yeah. It exists, but it's not allowed. Yeah. Yeah, so there are some locations in memory that you cannot access or the system will prevent you from trying to access. And one of them is memory location 0, because there's a lot of code corresponding to the system and booting up the system located at address 0. So what will try to happen is if you try to access the contents there, then the program will actually crash. And so exit code 11 means something called a segmentation fault, which means that something horribly went wrong, you did something completely wrong here. Usually means that you're trying to access some memory that you weren't allowed to use. So that's why I get an error here. But the issue here is not the cout, but rather that I can do this. I can assign this horribly null thing into a pointer. So what is a better way? So for some reason, I didn't have this in the slides. I re-uploaded some slides this morning. The next slide is the change. So in a recent version of C++, namely 11, there's actually a better way to do this exact same thing, which is something called null putter. So that if I try to use null putter instead, so remember, null itself is 0, but null putter is the same thing, but the difference is 0 is what type? What is the type of 0? Usually, int. So here, null putter means no type at all. It's not a type at all. So what happens here is if you try to use null putter, what'll happen is it'll give you some nice exception handling if you handle it correctly. Whereas if you use null instead, you don't have any way of being able to mitigate against that. So if you really have to initialize a pointer to nothing at the start, use null putter, not null. Okay? Yeah, so I highly advocate doing it this way if you're using pointers in the first place. It just indicates that it doesn't contain a valid memory location. Fine. But if we want to actually work with pointers, one pointer and another pointer, then we can do equality here. Because remember, the pointer itself is just an int. And so therefore, I can work with ints in the same way we've been doing all along. So if I do putter1 equals putter2, that compares the two addresses. Okay? So remember, putter1 and putter2, those are an address to some location in memory. So this right here will check, are putter1 and putter2 pointing to the same place? Which may be something you may want to check. But more often, we want to know, is the value of what putter1 is pointing to the same as what putter2 is pointing to? And then what we do instead is we dereference one pointer and the other pointer, and then check the values. So some cases you may want to do the first option, but most cases you want to do the second option because you want to compare the values of the things being pointed to. Any questions so far? Okay. But the usual place where pointers are used is to pass data along. So remember the reference operator, the ampersand, we have used sometimes in some function parameters where we just pass the address along. We can do the exact same thing with pointers. So it's actually no different here. But the thing is, if we use the reference parameter, then if we do some modifications on the variable, then that modifies the original, the one that was passed in. If we use a pointer instead, we have to dereference it first, but effectively we can do the same thing. So if we pass a pointer and you want to change the value of the original thing, then you want to have to dereference it first. But you could, for example, modify the actual pointer address so it points to somewhere else if you need to. That you can do without dereferencing. So yeah, so you can have a function like getNum or something where you pass the pointer along, and then so that's how you pass pointers. If you have a pointer initialized to null putter, I hope, first, and then we want to see in some value to put at that memory location, whatever it is, then maybe we want to cin it, and then we would have to dereference it. So I can't just do cin to putter because that would cin to the address, and we don't want to change the address necessarily. Sounds like a security bug. So like if you didn't put this star here, that would be like setting the address of some memory location, which you don't want. You want to change the value at that place. But we can use the ampersand to mean the reference if we wanted to. So remember this swap function for bubble sort and for actually selection sort too. So remember we had to make this temporary variable, move one of the values into the other variable, and then move from the temporary to the first variable so that we swap the two values without having to lose one of the two. You can do that with pointers also. So there's actually no difference here to the original code. The only difference is that in terms of what it does. In terms of the code itself, all we do is our passing pointers and then dereferencing as the case may be. But there's nothing special happening here. So I could pass, so the pointer has to be given an address because I'm passing a pointer here. So if I pass the address of num1, address of num2, then it'll swap the two values because we're dereferencing along the way. But we can pass whole arrays as pointers too. So we don't have to pass the entire array. We could either pass in a reference or pass a pointer, depends on what the best case scenario is for what we want to do. So if we have an integer array, then we could pass an int pointer. If we have a string array, we can pass a string pointer. Depends on what we're doing. But remember, the pointer itself could point to a single integer or it could point to a whole bunch of integers. The pointer itself doesn't tell you anything. All the pointer says is, what thing are you pointing to? Are you pointing to an int or a string or whatever? It doesn't tell you whether you're pointing to an array or not. And actually, what you could do in the case of 2D arrays, you can pass in what I call a double pointer, which is an int star star of something, which would mean that you have a pointer, which is pointing to a pointer, which is pointing to an int. So you can actually get this pretty deep, depending on how big the arrays you want to make here. Yeah. So you can pass whole arrays very easily this way. But sometimes we want to have const data or something like that. So like we have some tax rates and we don't want the tax rates to change, then we, as we have already done, we make const out here mean I don't want to change any values in here. Okay, so I want this thing, I want all these three values to be exactly the same and never change. Yeah, so putting const prevents modification. But what if you want instead that, remember when we can pass in a pointer and we could technically change where the pointer is pointing to? Maybe you don't care about the value staying the same, but you want the pointer's location to be the same. So you want whatever address this pointer is pointing to not change address to go somewhere else. Okay? Maybe you want that to happen. Or maybe you want it to point to the same location and the value to not change. Okay? Maybe you want that too. So here's what you do. So the way that you read these is from right to left. Okay? So if we look at this thing is called rates, and it's a pointer, so we're reading right to left. It's a pointer that's pointing to a const double. So a double that doesn't change. So the double itself, the thing it's pointing to, does not change. What about the pointer? Can the pointer change? Not the value, the pointer itself. Yeah, so I haven't said anything about the pointer. The pointer can change. The value cannot change of what it's pointing to. So what we do instead is we make a constant pointer. And the way you do that is after the star, you put const. So if we read right to left again, we look at, okay, this thing is called class putter, and it's a constant pointer to an int. Okay? So let me ask you this. So can the pointer change for class putter? Can the pointer itself change? Like, could I move this pointer from here to over somewhere else? No, because I said that this is a constant pointer. Can the value of what it's pointing to change? Yeah, why? Right, because it's pointing, the pointer is constant, but the int has not been declared constant. Okay, so the value at class size can change easily. So if I quickly show you a demo of this, so if we move this into here, so let's just see if we try to change class putter by 1. And this will not compile because, it was declared with a constant pointer here. But could I do star right here? Yeah, so if we actually print and we dereference class putter to see what value is actually there, then we can see that it prints 25. So the value of where class putter is pointing to, that can change. But what if I didn't want it to change? What would I have to do? Right, I would have to put const out here. And then now this won't compile because now it's pointing to a constant integer. So then if we try to print this, it'll print 24 as we expect. Any questions on how that works? So the way that you read pointers, just to reiterate, is you read right to left. I don't know why they did it that way, but that's the way that they've chosen. So here it's a constant pointer. The pointer itself is constant, and whatever it points to is a constant integer. Okay? If I remove the const here, I can't change class putter plus equals 1 because I declared it to point to a const int. But if I remove the dereference right here, I can move the pointer wherever I want. So if we do this, then it turns out that that memory location happens to be all zeros. But we can't guarantee anything from that. any questions before we break for today? All right, I'll see you on Friday.